The megastructure is a single construct of almost unimaginable scale. Current contenders for the megastructure mantle on Earth include the Great Wall of China, as well as some of the world's tallest skyscrapers, like the Empire State Building, Shanghai Tower, or the record-breaking tallest building itself, Dubai's Burj Khalifa. But when we move the focus away from our own planet and into space, there are seemingly no limits to how big we could theoretically build with enough time, resources, and knowledge. Currently, only one megastructure candidate exists beyond Earth, the International Space Station. But though the ISS is absolutely one of the most impressive things we've ever built, it's still not particularly big. It's only 357 feet long, and that's seriously small fry compared to what we hope to build in the future. Broadly speaking, theorized space-age megastructures come in 4 categories of size, with the smallest being transorbital structures. Most transorbital structures are imagined as a way to propel vehicles and people into space, and by far the most popular so far planned is the space elevator, an enormous tube that could, in theory, continuously ferry objects into orbit. The main benefit of a space elevator is that with it, we wouldn't need to use rockets anymore to leave Earth. People and things would now be carried into orbit via a relatively simple mechanism. We'd easily hop into the elevator, choose our desired altitude, and arrive in space at the end. No need for the costly, potentially dangerous, and environmentally damaging rocket launches of the past. As exciting as this idea is, however, it's not all that practical. The Kármán line is generally considered to be where Earth's atmosphere ends and space begins. It's 62 miles up. So to get into orbit, we would need a 62-mile-long elevator. Today, the world's longest elevator is at a gold mine in South Africa. It measures at just over 1.4 miles long, and that's 1.4 miles down into the ground, not up into the sky. As of the early 2020s then, we simply don't have a material remotely strong or flexible enough to actually build a space elevator. We would need something that can safely function and reliably withstand the speed of the Earth moving through space. Carbon nanotubes could be our best bet at the moment. But while they do exist, they're also extremely expensive to produce and at present impossible to make on the scale needed. We're also in totally uncharted territory here, so really there's no reason to think that even carbon nanotubes definitely would be strong enough. We could well need something else, something better, and something that hasn't even been invented yet. If we could build a space elevator though, it'd be used not just by space agencies for cheaper and easier space exploration, but for tourism too. And all of those tourists are going to need a final destination. The next size of megastructure is known as orbital, and arguably the ISS already counts as being within this category. But we're expecting to see much more than just the space station in the future, with various plans for far bigger, more ambitious, and more opulent orbital habitats. For decades, scientists and designers have pitched increasingly viable plans for orbital space colonies. But the most famous comes from the Princeton physicist Gerard K. O'Neill in the 1970s. Called O'Neill cylinders, these designs, like many similar ones, rely on a vast centrifuge to create artificial gravity. This centrifuge is really the key bit of technology needed to make it work. O'Neill cylinders would be large, round, and they'd rotate, with this rotation working to provide the gravity. One of the best things, though, about centrifugal gravity is that it potentially works just as well, if not better, with larger objects than smaller. So it'd actually be within our best interests to build vast, city-sized structures of this type, capable of housing thousands of people. Within the cylinder, hydroponic farms would provide food, while shuttle runs from Earth could top up other additional supplies. Orbital cities like this might prove a little challenging to live on full-time, especially for the earliest generations, but they'd also be an astounding and lucrative short-term tourist destination. O'Neill's ideas haven't been lost in the 21st century either. Today, Jeff Bezos and Blue Origin have set out plans to build a new age of space habitats based on O'Neill's designs. If you had the chance, would you want to live somewhere like this? With space elevators and orbital stations in place, however, we can swiftly begin to look even further afield for the next type of megastructure, a planetary structure. This is, as you'd expect, something the size of a planet. The most famous planetary megastructure in science fiction is, of course, the Death Star in Star Wars, a world-destroying superweapon. But while it's depressingly easy to imagine humans building an enormous weapon like this, there are non-destructive planet-sized options we could build as well, like shell worlds. Shell worlds are an ambitious, theoretical terraforming method, where an entire, otherwise inhospitable planet is enclosed in a spherical shell, which would create an artificial atmosphere, if pumped full of the right gases. this would be a massive undertaking. But when some of our other ideas for potentially terraforming another planet involve nuking it to oblivion, shell worlds perhaps start to look like a more attractive prospect. Again, the materials needed aren't exactly certain at the moment, but most designs involve the shell being transparent so that the sky is still visible for anyone living within them. In theory, these structures could make any planet hospitable to humans. And were we to build multiple of them, then we'd essentially have a net of human-friendly bubbles dotted about space. In some cases, it's thought we wouldn't even need a planet to begin with. That we could build these megastructures from scratch, wherein one shell encases another one, and we live in the space in between them. Shell worlds are a far future dream, but what a dream it is. Lastly though, we have one final step to make. And while a planet definitely is large, planet-sized structures still aren't the biggest we could build. Stellar megastructures theoretically exist on the stellar scale. These are the size of stars, and stars can be truly gigantic. Already, the Sun is the largest object in our solar system, but one of the biggest stars ever discovered, Scuti, has a radius more than 1,700 times greater than the Sun, and it's 30 times more massive too. Stellar engines are imagined megastructures that would harvest the power created by a star and convert it into energy we could actually use. The most famous is the Dyson sphere, a large structure built around a star that siphons off its energy, providing an unprecedented power source. Nuclear fusion is the reaction that happens within stars to keep them burning. We have artificially created fusion reactions on Earth before now, but they're so extraordinarily expensive and difficult to achieve that they aren't yet a viable power solution for humankind. Build a Dyson sphere though, and we needn't worry. We no longer have to artificially generate fusion. We could just tap into where it happens naturally. But arguably an even more outlandish idea than that is a Shkedov thruster, which would use the energy of an entire star specifically for propulsion. Shkedov thrusters, like everything else in this video, are totally theoretical right now, but there are some ideas as to how they could work. Once again, we'd be bleeding energy from a star, but then there'd be a huge hemispherical mirror, or light sail, to reflect that energy in whatever direction we desired, to create thrust and give us control. The scale of engineering we'd be dealing with here is astronomically huge, literally, but the benefits of the Shkedov thruster are similarly gargantuan. With one, we'd be able to travel at the incredible speeds that stars already travel at. The fastest star we've ever discovered, S4714, is currently flying through space at about 8% the speed of light. That's 15,000 miles per second. So imagine hacking into that level of power. To some, it's beyond belief, and it's certainly far beyond our capabilities at the moment. Realistically, we need the first breakout of the solar system before it can even be considered a possibility. But isn't that the beauty of theoretical designs like these? With enough time, resources, and knowledge to design and build stuff, there's arguably no limit to what we could create. But those are 4 especially exciting theoretical megastructures ranked from big to massive.